Welcome to Chapter 1 of Quantum Computing Hardware. The introduction series treated a qubit as a mathematical object, a two-dimensional vector that gates rotate and measurement collapses. This series asks the harder question. What does it take to build one out of matter, keep it alive, talk to it, and read it back on thousands of copies at once? This chapter contains almost no device specifications, and that is deliberate. Hardware numbers age badly. What does not age is the physics. The requirements any candidate system must satisfy, the tension those requirements create, and the figures of merit that let you compare platforms honestly. A qubit is not a thing you find. It is a role a physical system can be made to play. Almost anything with two distinguishable quantum states is a candidate: an electron spin, an atom in its ground or excited state, a photon in one path or another, a superconducting circuit. In the year 2000, David DiVincenzo set out what a candidate must actually provide: scalable, well-characterized qubits, reliable initialization, decoherence times long relative to the gate time, a universal gate set, and qubit-specific measurement. Two further criteria, converting and transmitting flying qubits, are what modular linked processors depend on. Here is the difficulty that shapes every design decision in this series. Criterion 3 asks the qubit to be isolated because decoherence is the loss of quantum information into the environment. The ideal qubit talks to nothing, but criteria 4 and 5 ask the qubit to be controllable. Gates, readout, and entangling operations all work by coupling it to something. The ideal qubit talks to everything you choose. These two demands pull on the same physical coupling, so no amount of cleverness escapes the trade. What engineering can do is make the coupling selective, strong at the frequency you drive and weak everywhere else. Four quantities describe the health of a qubit. T1 is the timescale on which an excited qubit loses its energy to the environment and decays toward the zero state, like an excited atom emitting a photon. That loss is irreversible. T2 is the timescale on which the relative phase between 0 and 1 becomes randomized. Dephasing is the more insidious of the two because it destroys the resource without destroying the energy. The two are linked by a strict inequality. 1 over T2 equals 1 over twice T1 plus 1 over the pure dephasing time. So T2 is at most twice T1. Fidelity measures how close the operation you performed is to the operation you intended on a scale where 1 is perfect. The error rate is 1 minus the fidelity, and it accumulates across a circuit, so the affordable depth is of order 1 divided by that error rate. Two cautions when reading fidelity claims. Single qubit and two qubit fidelities are very different quantities, and a headline number that does not say which is not telling you much. And fidelities measured on isolated pairs degrade when the whole device runs at once. Gate time, quoted on its own, means nothing at all. So here is the honest comparison. Divide the coherence time by the gate time, and you get how many gates fit inside a coherence time. This is DiVincenzo's third criterion made quantitative, and it is the number to look for. Take two hypothetical platforms with round teaching numbers rather than measurements. Platform A has a coherence time of 30 microseconds and a gate lasting 0.02 microseconds, so about 1,500 gates fit inside. Platform B has 100 times the coherence but 1,000 times the gate duration, and fits only 150. A qubit count tells you none of this. A quantum computer is not a chip. It is a stack of 4 layers. At the bottom sits the quantum layer, the physical qubits and the structures that couple them. Above it, the analog control layer turns an abstract gate into a physical stimulus, a shaped pulse or a voltage waveform, because a gate is its pulse. A rotation angle is set by a pulse area, so an amplitude error is a rotation error. The digital electronics layer sequences those pulses and closes feedback loops fast enough for error correction. At the top, the compiler maps and routes circuits onto this specific device. An algorithm designer draws a 2-qubit gate between any pair. A chip designer must decide in advance, and in metal, which pairs are physically coupled. Solid-state chips are typically nearest neighbor, while systems coupled through a shared mode can be all-to-all. When your algorithm needs a gate between qubits that are not connected, the compiler moves the information with swap gates, and one swap costs 3 CNOT gates in the usual decomposition. On a grid, a typical pair sits about the square root of the qubit number apart, so routing gets worse exactly as the device grows. Let us make decoherence concrete, using only NumPy. The timescales here are round teaching numbers, not measurements of any device. Take T1 as 60 microseconds and pure dephasing as 40. Because the two channels add as rates rather than as times, T2 comes out at 30, shorter than either input, which is why hardware work so often means hunting down the single worst noise source. Now raise the pure dephasing time. T2 climbs toward the ceiling of 120, which is twice T1, reaching very nearly all of it, but never crossing. The inequality is a numerical fact. Let's recap. The Dai-Vincenzo criteria define what any platform must provide, including decoherence times long relative to gate times. The central tension is that coherence demands isolation while gates and readout demand coupling, and both act through the same physical channel. We define T1 for energy relaxation and T2 for dephasing, with the strict ceiling that T2 is at most twice T1, alongside gate fidelity and gate time. The honest figure of merit is how many gates fit inside a coherence time. We walked the 4-layer stack and saw connectivity charge swaps at 3 CNOTs each. Next, superconducting qubits.